My current work is motion detection from moving camera drone. This work will be submitted in ICRA 2017. In this work, we focus on real-time robust motion detection. Background subtraction with motion compensation is commonly used because of its efficiency. As the figure shows, the background subtraction calculates the foreground mask, performing a subtraction between the current frame and the background model after motion compensation. Background subtraction works well if the background can be approximated as a single plane. However, it may suffer from the following issues. First, the background subtraction can handle strong parallax. Second, the dynamic background is misidentified as moving objects. In order to address these challenges, here are our contributions. First, we proposed a dual-plane model to represent the scenes in aerial video. We introduced the initial information to estimate the homography based on this model. Second, we propose a novel probabilistic model to describe the uncertainty in foreground appearance, which can efficiently distinguish the independently moving objects from dynamic background. Third, we create and public a dataset which includes the videos taken from a drone camera with synchronized initial information of the drone. First, we use dual plane to model the background to handle the strong parallax in aerial video. That is, given two images taken at different times, we use two planes, front plane and ground plane, to model the background, distant view, and ground view. This model simplifies the layer-based model of strong parallax without losing detection accuracy. Because the depth disparity on each plane is relatively low compared with the distance from the camera drone. Based on this model, here's our framework, including two key modules: dual-plane homography estimation and dual-plane foreground modeling. For dual-plane homography estimation, our intuition is straightforward. First, a subset of point correspondence is computed by ransack, fitting one specific homography. Second, after excluding previously calculated subset, we perform ransack again to find the next layer of homography for the residual feature points. In our scenario, the goal is to extract two homography matrices for front plane and ground plane. Assume that aerial image is dominated by ground. This homography is induced by corresponding points on ground plane. Usually, corner detectors such as Harris are utilized to extract features, followed by a robust estimation technique such as ransack. However, this approach is not suitable for some environments, such as this image, because this technique would render few points on the homogeneous ground, compared with moving objects and other objects on the background, which have richer corner content. Instead, we uniformly and densely sample the points from frame and perform KLT on every sample point to get the point tracking results. Finally, we perform ransack to obtain a homography matrix. With point correspondence, we estimate the dominant homography by ransack. The ransack will label these points as inlines and outlines. Here, inlines are blue point. The outlines are red point. Secondly, after excluding inlines, we perform ransack again to find the next layer of homography for the residual point. However, dominant plane homography estimation becomes difficult as the percentage of outlines from ransack is high, resulting the corruption of secondary homography estimation. As image shows, the incorrect homography will result in false motion detection. In addition, the homography estimation may suffer from large motion blurs caused by fast movement or long exposure time of a camera. IMUs can measure the angular and translation information of a camera with few restrictions on the object appearance. So we can use it to help improve our homography estimation. Here, we propose to use the prior knowledge of the scenarios and the initial data obtained from IMU to calculate the homography. Here, input is the pose information of a camera at different times with regard to IMU frame. The output is the homography transformation with regard to camera frame. Let us consider drone flying on a flight plane with normal vector n. The camera on the drone looks forward to the plane at time ta with initial rotation Ra and height Ha with respect to the IMU coordinate system. Then, a rotation R and a translation T occur at time Tb. Given the camera calibration matrix K, the homography matrix between Ta and Tb is calculated as follows. Also, the accuracy of inertial data usually decreases over time due to accumulated drifts. We employ common filter to fuse visual and inertial measurement to combine the complementary advantages of these two solutions. In this image, HV is a vision-based homography. HS is inertial-based homography. More precisely, we introduce process model. The filter state vector xt is predict homography from initial time to time t. The state transition matrix ft is initial homography from time t minus 1 and time t. Wt is a Gaussian distribution modeling the inertial noise. The process model is essentially the multiplication of two homography for adjacent time periods. For observation model, the observation vector zt takes the value of vision ground homography matrix from initial time to time t. Bt is identity matrix. Vt depends on the point correspondence. Considering that the accuracy of vision homography estimation is related with the ratio of outlines and inlines, we use an adaptive Gaussian distribution to tune the visual noise parameters accordingly based on the ratio of outlines and inlines. Homography updates rule is the same as the standard common filter. The difference is that the Gaussian variance Pt of vision noise is adjusted at each iteration. Once the fused homography is computed, it's necessary to relabel the inlines and outline. That is, it's a point pair will be considered as an outline if it does not fit the fused homography matrix. After excluding inlines, we perform ransack again to find the secondary plane homography for the outlines. This image shows that the motion detection has been improved after relabel the inlines and outlines. The second part is dual-plane foreground modeling. This module includes two steps. First, we do the foreground modeling for each homography. Second, we compute the intersection of both results to output the final mask. To extract the foreground, the basic idea is all the moving objects which are subject to different homography transformation are identified as a foreground. However, because of parallax and dynamic background, we need to add a module to refine the initial result. Our method is inspired by paper published in ICIP 2015, which defines the probability of a foreground object. The foreground probability is the multiplication of temporal and spatial properties. Temporal properties, PT, is defined as a recent history of foreground at each pixel position. DT is defined as a binary map output by background subtraction. DT is 1 if pixel m belongs to the moving object at the time t. Alpha is the temporal learning rate. Spatial properties PS measures the coherency of nearby pixels of foreground. NN denotes a spatial neighborhood around the pixel n, and W square is the area of neighborhood. Beta is the spatial learning rate. However, the pixel-wise spatial and temporal properties are not enough to distinguish the dynamic background. Temporal properties only eliminate the twinkle fake moving pixel. Spatial property only removes the discrete points. Based on the above discussion, our intuition is to add the grid-wise constraint. We make the assumption that the motion of our moving target should be smooth spatially and temporally. Look at the left image. The waves are misidentified as moving objects. If we calculate the optical flow, we can see that the object's sailboat has consistent optical flow. In contrast, the optical flow of waves are very random. From the perspective of information theory, it has large entropy. So our intuition is to combine these properties to identify the moving objects. First, we divide each frame into multiple equal-sized grids. Second, we perform KLT on the pixels uniformly and densely for optical flow estimation. For each grid, an orientation histogram with 12 beams is formed. Each beam covers 30 degrees. Here in this image, it shows that the orientation histogram of dynamic background indicates in purple box is smoother than that of a sailboat, indicate in red box. We can use reciprocal entropy to measure the consistency of optical flow for each grid. Here the PBI is the probability of the S-beam. The pixels within each grid share the same reciprocal entropy. We combine the temporal consistency, spatial consistency, and the entropy consistency to express our absorption of moving objects. The foreground probability, PFG, is defined as the multiplication of temporal, spatial, and entropy properties. The pixels with foreground probability smaller than a threshold are removed from initial result. Here is a final pipeline that our foreground refinement is a probability model involving temporal, spatial, and entropy consistency. In this work, our datasets are recorded on DJI drone in outdoor environment, including 6 video clips synchronized with inertial data. Each clip is about 10 seconds. The red image is the camera trajectory reconstructed from IMU data. First, we evaluate different modules in our structure. The accuracy is measured by precision recall curve. The experimental results show that the dual plane model, inertial fusion, and foreground refinement can improve the motion detection without increasing too much computation. In this part, we compare our method with 2 state-of-the-art methods. ICIP 2015 applied 2 single Gaussian models to represent the probability of a foreground and a background of each grid separately, and then spatial temporal properties are utilized to refine the foreground results. WACV 2016 implemented multi-view geometry constraint based on the epipolar filter to detect moving objects. Experimental results show that our proposed method can balance the precision and recall while maintaining real-time computation. In this experiment, we compare our method with inertial aided motion detection published in IROS 2015. These algorithms combine the visual and inertial measurements to segment the outlines from consistent optical flow as moving objects. Experimental results show that our proposed method can perform better than the state-of-the-art inertial-aided method in strong parallax outdoor environment. Finally, we run our algorithms on Snapdragon flight board during flight. Here we test the video clip with smaller size. This table shows that the performance on drone can approximate real-time computation.